In this problem, we have a mass that is at rest on a horizontal surface, and it's acted upon by two external applied forces. A force at so many degrees up and to the left, and another force at so many degrees up and to the right. You can see in the picture here, this is my abbreviation for force up and to the left. And on the other side, that's my abbreviation for force up and to the right. The coefficient of static friction is given, and the question is, will this mass move? Well, let's draw a free body diagram. We'll put the weight in there, goes straight down. We have a normal force that's pointing directly upwards. We don't know necessarily how big it is, but we do know that it points upwards, and that's the main thing for now. These applied forces are neither parallel nor perpendicular to the surface, which means that we need to resolve them into parallel and perpendicular components. So hopefully you can see here that the force up and to the left will require the use of the sine of theta to find the vertical component, or the perpendicular component, and the use of the cosine to find the parallel component. Same thing on the other side. Now we also have static friction. We don't know which way static friction acts, because it's going to depend on the relative magnitude of this leftward pointing green arrow compared to this rightward pointing green arrow. In short, the friction force is going to help the smaller of those two. So let's just pick a direction for the static friction force and go from there. Now let's go to Newton's second law. We're going to first sum the forces that are perpendicular to the surface. Upward is positive, so of the four perpendicular forces, you can see the only one that's negative, that is the only one that points downward, is the weight. And according to Newton's second law, the sum of those perpendicular forces should equal the mass of the object times the acceleration perpendicular to the surface. Well, the acceleration perpendicular to the surface is going to be 0, so the right side of this equation becomes 0. We're given the force up and to the left. We're given the angle at which it acts. Same with the force up and to the right and its angle. We know the mass, we know g, and that means that the only thing that we don't know in this equation is the normal force, which means we can use these other quantities to calculate that. Now, static friction could range from a value of 0 to some maximum value. And the maximum value that the static friction force could have is equal to the coefficient of static friction, which we're given, times the normal force, which from this first Newton's second law equation we are able to calculate. Therefore, we could calculate the maximum amount of static friction that is possible in this situation. Let's write the other Newton's second law equation. I've chosen to the right to be positive, so the force up and to the right times the cosine of phi is positive. The force up and to the left times the cosine of theta is negative because it's pointing the other way. And the way I've drawn it in the free body diagram, the required static friction force is positive. That should equal the mass times the acceleration parallel to the surface. If we don't want this mass to move, the acceleration should be 0. We know the applied forces, and we know the angles, which means we know everything in this equation except the required static friction force. So what we're going to do is use this bottom equation, calculate the required static friction force, and compare it to the maximum static friction force that's possible. If the required static friction force is less than the maximum that's possible, then no, the mass will not move. If the static friction force that is required in order to keep this mass at rest turns out to be greater than the maximum that's possible, then yes, the mass will begin moving.